Jeff Ligarius, a mathematician I admire a lot, thinks it's one of the hardest problems around. Erdős actually said, this is a problem for which mathematics is perhaps not ready. Turns out all this fuss is about a problem that any fourth grader can understand. To show you how this all works, I'm going to give you an example. Brady, choose a number between 1 and 10.
I shall go for 7.
All right, let's start with 7. Now, I'm going to apply 2 rules depending on what number I get to. I'm going to do this in succession. And if n is even, then I'm going to take n and divide it by 2. If n is odd, then I'm going to take n, can't divide it by 2 and get a whole number, so I'm going to take n and multiply it by 3 and add 1. Those are my rules. And I'm interested in what happens to n. Does it grow to infinity? Does it get small? Let's see what happens with 7. 7 seems to be an odd number, so I multiply by 3 and add 1. 3 times 7 is 21. Check me on this. And add 1 is 22. I go to 22. 22 is certainly even, so I'll divide by 2 and get 11. 11 is odd, so I multiply by 3, getting 33, and add 1, get 34. 34 is even. I divide by 2, and I get 17. So far it's sort of going up and down. But 34 was the biggest yet, so maybe it's headed off to infinity after all. 17. So 17 is odd. I multiply by 3. 3 times 10 is 30. 3 times 7 is 21. 51 plus 1 is 52. Even. Divide by 2 and get 26. Still even. Divide by 2 again and get 13. Now it's odd. Multiply by 3 and add 1. 40. 40 is even. I divide, I get 20. I divide again, I get 10. I divide again, I get 5. Boy, we fell down a long way. Maybe we're heading for a small number after all. Multiply by 3 and add 1, I get 16. Whoa, 16, very even number. I get 8, I get 4, I get 2, and I get 1. If I do it again, something interesting happens. I go 3 times 1 plus 1 is 4. Whoops, I'm back to 4. But now I'm just going to cycle forever, going through 1 over and over again. So I got to 1. 7 got to 1. Now, people have tried lots of numbers beginning this way. And so far, all of them have gone to 1. They've tried roughly 2 to the 60th numbers. That's almost 10 to the 20th. So the famous Kolátz conjecture says that every number, every whole number will eventually get to 1. And a huge amount of work has been done on this problem by combinatorialists, by number theorists. This is the problem that maybe mathematics is not ready for, but that any fourth grader could play with and try, right? Try some numbers. First of all, we'd like to understand what's happening in such a way that we can say for certainty that every number, all the numbers we haven't ever tried, will get to 1. You could just try this on your computer. It's a good test for your personal computer, too. How fast a program can you make? Here's a little hint. Every time I take an odd number and multiply by 3 and add 1, I get an even number. So why not take 2 steps at once to 3n plus 1 over 2. Combine those 2 steps when I get an odd number. That speeds things up a bit. And there are other tricks like that. So people make graphs like this, and they're called trees, right? So far, all the numbers go down to 1. But we might start with another number. If we started with 5, we already see what the answer would be. Any number that appears here, we already know the answer. We don't have to do it again. What's the first number that doesn't appear here? I think it's 6. Shall we try 6?
Let's do it.
Let's do it. Okay, 6. And 6 goes, well, it's even. Goes to 3. 3 goes to 10. Have we got 10? Whoops, there's 10. So I should just draw the 3 going down to 10 instead. And now I know I'm beginning to build up my tree. I've tried now all the numbers up through 7, 8 I've got. 9 I thought I had somewhere. Didn't I have a 9?
I can't see a 9.
No, I don't see a 9. Let's try 9. Yeah. So 9, okay. Odd number. 3 times 9 plus 1, 28. 28, 14, whoops, 7. Where's my 7? There it is. It goes to 7. So I can begin doing this and build up my tree. I don't have to go all the way each time. I know what's going to happen after I get to 7. If you look at the cover of this book that I showed you first, that's a tree of just this kind. But people have built up huge trees of this kind. And there's a wonderful article on Wikipedia that you can look at which shows some of the pictures of this.
There does seem to be a very striking feature of it, and this is this line down the middle here.
That's right. This is like the third rail. Once you touch that line, you fall right away to 1. By the way, there's another name for this problem, which is the hailstone problem. And the reason is, as you probably know, when hailstones form in the clouds, the way they form, the way they get bigger, is that they start low and they get blown up by the winds and they get some ice on them and they fall down a bit and then they go up and down. They go up and down many times and finally they fall to earth. If they never get to earth, of course, they're not hailstones. And it's just like numbers here. They go seemingly randomly up and down and then eventually they seem to fall to 1, to the ground. What kind of things have people done with this funny problem? Well, they've compiled, for instance, records. I got a long string with 7. What's the next number after 7 which gives a longer string? Well, it's not 8. 8 is down here. We found it already. It's 9. 9 only goes through 7. What's the next number after that? Well, you can look on the online Encyclopedia of Integer Sequences, that great resource, and you'll find a table of the record-holding numbers. You'll also find a table of the numbers that hold the record for the longest time to get to 1. Let's get a couple of examples here. There's some wonderful ones. For instance, the record holder for the numbers under 100 million, people know all these things, is 63,728,127. And that takes 949 steps to get to 1. I bet the person who found it thought maybe he was onto something, maybe he finally had a counterexample, but no. So there are records and records and records, and people have tabulated this looking for patterns that might help them understand what's really going on. So the randomness of this is what seems to make it hard, the fact that we don't see a pattern, and that no matter how hard you look, the patterns you see tend to be illusory somehow. They melt away when you look further, or you don't understand them. Like the pattern of always going to 1. That one holds sure, but we don't understand why it's there.